Welcome to qnawire.
Angular momentum is conserved in the interaction between the child and the merry-go-round because there is no external torque. Therefore, Li is equal to Lf, where I stands for initial and F stands for final. Therefore, Li of the child plus Li of the merry-go-round is equal to Lf of the child plus Lf of the merry-go-round. And since the child is at rest initially, therefore this goes to 0. Now angular momentum is given by I times omega. Therefore, for the merry-go-round, this will be equal to I of the merry-go-round times omega of the merry-go-round initially, which is omega naught. And this is equal to LFC plus LFM, and LFC is moment of inertia of the child times omega, where omega is the final moment of inertia after it slows down, after the merry-go-round slows down, and also LFM will be equal to Im times omega. Since the child is on the merry-go-round, they slow down and they have the same angular velocity. So we take the final angular velocity out of the expression. So this is what we got. Now the moment of inertia of the child is just mr square. And r is the radius of the merry-go-round, because let's say this is the merry-go-round and the child is sitting and on the circumference of the circle. Therefore, from the center its distance is r, and since the moment of inertia is taken about the axis, therefore the moment of inertia of the child will be equal to mass of the child times square of this radius. So we write that over here. Now from this expression we can solve for the mass of the child, which will be equal to Im times omega naught minus omega, basically the difference between the initial and final angular velocities, over r square, radius of the merry-go-round, times omega. Now given these values, we can solve this expression now, and we get the mass of the child to be equal to 73 kgs.